So it is a very important thing of the fluid dynamics, the convection. Okay, so see, we know that a fluid can be in a mechanical equilibrium without being in thermal equilibrium. Okay, so if there is a fluid and there is a mechanical equilibrium, and no thermal equilibrium. Okay, so it means total sum of the force on the system is zero, uh, but heat can flow. Okay, so the system is not in a thermal equilibrium. So if it is so, then we know that there is a condition. The condition is this: grade P is equal to rho g. Okay, or sometimes you can write it down as a dP by dz is equal to rho g. So this condition for the mechanical equilibrium can be satisfied. Okay, even temperature is not constant due to the not thermal equilibrium condition. Okay, so this condition is valid due to the mechanical equilibrium, and temperature is not constant throughout the fluid. Okay, so but the question is arise of the stability of such kind of equilibrium. And we know that the equilibrium is stable, okay, only when there is a certain conditions are fulfilled, otherwise system will be unstable. Okay, and due to this condition, there is some kind of mixing in the fluid, so it tries to equalize the temperature, mean the system wants to be in a thermal equilibrium. Okay, so initially system in a mechanical equilibrium, and finally system want to be in a thermal equilibrium also. Okay, so this condition is known as the convection. This is the definition of the convection. Okay, in which system wants to be in a thermal equilibrium to equalize its temperature. Okay, so thus the condition for a mechanical equilibrium to be stable is the condition that convection be absent. Okay, so let's derive this condition. Okay, so suppose there is a fluid element at height z. So at height z there is some fluid element, and there is some specific volume. Volume of this fluid element is V, where P and S are the pressure and entropy at height z. Suppose that this fluid element undergoes an adiabatic upward displacement. Okay, so it moves very fast in upward direction, so it is an adiabatic upward displacement, and the interval is very small. Okay, and its specific volume becomes, so this P prime S. Why? This P prime S is a pressure at height this. Okay, this height is z plus zeta. So here volume is same, but pressure is little bit different. Okay, for the equilibrium to be stable, it is necessary that the resulting force on the element should tends to return its original position, like a spring or like any small oscillation. This means that the element must be heavier than the fluid which is displaced. Otherwise, system will not come back to its original position. Okay, just like in the pendulum case. Okay, pendulum is moving there, and after some time it's come back. So similarly, it should be come back in its original position. The specific volume of the final, the later one, is this V P prime S prime. Now S is also changed. What is S? S is the equilibrium entropy at the height z plus zeta. So what is the stability condition? It means stability condition is this: the volume at p prime s prime should be greater than the volume at p prime s. Okay, it is the condition. Okay, then it come back. So it is a stability condition. Okay, and we can expand this difference in terms of the power of s prime s. Difference means this minus. So if you are expanding in terms of the power of the difference s prime minus s, which is nothing but zeta ds over dz. So we can obtain dv over ds, constant pressure, and ds over dz is greater than or equal to 0. Okay, we are just expanding around this equilibrium. And from the thermodynamics, we know that what is dV over ds? V is the volume and this is entropy at constant pressure. It is nothing but dV over dt and T upon Cp, where Cp is the specific heat at a constant pressure. Okay, it means this term, dV by dt, T by Cp should be greater than 0. See, put this value here. Put this value here. So it will be del V over del T. Of course, T upon Cp we should be there, and ds upon dz should be greater than 0 because Cp and T are positive. Okay, so we can write down in this term. Okay, and it's clear that the majority of substance expands on heating, means dV over dt is already greater than 0. So the condition in which the convection should be absent, okay, should be this. Okay, and or you can say that entropy must increase with height. If entropy is increasing with height, so convection is not there. So for the convection, entropy should not increase with height. Okay, from this we easily find the condition that must be satisfied by the temperature gradient Td over dj. So ds over dz is equal to ds over dt and dt upon dz plus ds over dp dp upon dz. So it is Cp upon T dt upon dz, and this is del V upon del T it is greater than 0. Okay, and we can substitute the value of dp upon dz. What should be the value of dp upon dz? It's a very simple. We know that dp upon dz is equal to rho g. So it means dp upon dz is a g by v volume. Okay, so we can put instead of this g by v volume, because 1 by volume means the density. So it means minus dt upon dz is less than g beta T upon Cp. Okay, just put it this side. Okay, and it is this. What is beta? Beta is thermal expansion coefficient. Okay, for a column of a gas in equilibrium which can be taken as a thermodynamically perfect gas, we know that beta into T is equal to 1. So it reduces in a very simple manner. Minus dt upon dz is less than g upon cp. So convection occurs if these conditions are not satisfied. If the temperature decreases upwards with a gradient whose magnitude exceeds the value given by this. Okay, so then only convection possible. So the main thing is this. So for the convection, uh, the temperature should be decreased with the height, and entropy should also decrease with height. Okay, if entropy is increasing with height, then there is a no convection. So temperature should decrease and entropy should decrease both. Okay.